all, being honored as an adjunct professor of your prestigious university. And of course, I'm happy to see a lot of colleagues and a lot of students, because science is nothing just for science, it's something for people. And people are first young people, as you are. You are the future of your country. That's why I'm happy to give this talk also to you, the students, and not only for the experts, which do already know a lot of things that I certainly do not know. I have first to apologize for Malayalam. I'm not sure if I translated everything correctly. Please tell me afterwards where I should improve. I'm sure there are things to be improved. But it's definitely true. My name is Pfeffer, means there is some historical relation, definitely, with this region here in India. But today's topic is something totally different, and it's dealing with nanotechnology, and nanotechnology when it comes to optical engineering. As has already been mentioned, nanotechnology has a special issue when it comes to optical engineering, because the wavelength, as we all know, is in the range of nanometers. So if we come down with structures below the order of some hundreds of nanometers, we have effects that we normally do not have, and that's where I want to speak on. So I have my topic in some aspects oriented. First, of course, I would like to focus also on the situation as we currently have it in the so-called nano industry. Then I'd like to focus on nanometric structuring for especially optical surfaces. I would like to focus on three aspects. The first is a technology so-called spin-on technology. The second one is all kinds of sub-wavelength structured anti-reflective coatings. That's what you mentioned, the Maathai Effect. And I would like to discuss this on the three different aspects. The first one is the anti-reflective structures in glass. The second one, anti-reflective structures on surfaces which are not plane, so means they are curved. And third one is anti-reflective structures calcium fluoride for deep UV applications. Deep UV is an abbreviation for deep ultraviolet wavelengths, which are beyond 180 nanometers or even below. And then non-wetting coatings for structured and unstructured optical surfaces play also an important role. As you may all know, if, for example, you drive today home with your car and your window is covered with dust, you're gonna have a lot of problems in order to see where's the road, because there is a lot of blurring. And this has to do with effects which are not on the real nanometric scale, but the effects come close to nanometric effects. So currently, the situation, we have few commercially available products with nanometric features. And you may ask why this is the case. I can show you. There is, from a design point of view, today's optical industry has a lack of knowledge and experience in that nanoscience domain, because they were working in the optics domain since centuries, I would say, with methods which are more macroscopic. So this approach to go beyond, let's say, some hundreds of nanometers is, in their mindset, new. Secondly, cost-efficient and reliable industrial production of nanometric structured surfaces require fabrication processes similar to those that we have today in semiconductor industry, which is also a different field, because these people come from a totally other approach. They come from an electronic approach. However, the fabrication at the end is similar or the same. And when it comes to testing, serial testing and qualifying of such kind of devices which have nanometric features require special testing facilities and instruments and tools. As you may all know, the so-called scanning electron microscope, the atomic force microscope, or other types of scanning probe microscopes. And they are not yet common standards among industries, because nobody really knows how to use and where's the problem when it comes to a nanometer. If I ask you, you are students, how big is a nanometer? How large is it? Like this, like this? Why is the nanometer called nanometer? Have you ever thought about that? This is a difficult question. I always ask my students that because my children ask me also the same question. They ask me, Father, what are you doing? And I say, I'm working in nanotechnology. And say, what's that? Tell us. I say, this is easy to explain to children. Nanos in Greek means a dwarf, a small person, a very small person. And you know, children, they think always in these fairy tale images. So I said, this is dwarf technology. It's dwarf technology, and so they understood it. And it's correct. It's somehow dwarf technology at an extent of 10 to the minus 9. So a 10 to the minus 9 meter is a nanometer. So for the gentlemen among you, a nanometer practically means when you start shaving in the morning here, when you're there, it has already grown here a nanometer. This is just to give you an idea. Okay, so we are now at the nanometer scale. You have now a feeling, at least if you have some beards here. And of course, nanostructured elements need a very careful handling with respect to pollution, packaging, and stockage. So these are things we are not yet used to handle with some experience. And in some, currently, all these aspects make optical devices with nanometrical structure surface to appear less interesting for commercial applications. Behind that, you see the sum of fears of things where people say, okay, why should I do this? Where is the advantage? So let us first focus on the so-called spin-on technology, SOG, I abbreviated. It was a collaboration with Professor Martin Geis in Lausanne and Dr. Jens Gobrecht also in Switzerland, and a company called Swiss Optic in Switzerland. And let me see what it is. For this spin-on glass technology, the requirements which came from industry, they said, we want to have, for an industrial applications, large areas, means in their sense 10 to 10 millimeters is large at that scale. For a diffractive area is opposite to a refractive area, an area which has certain structures in order to create diffractive effects. This is a typical size for optical sensor applications and typical maximum size for one diffractive element of an array. Secondly, they wanted to have a batch processing of nanostructured surfaces on a 4-inch wafer. All these wafers they are producing typically are 4, 6, 8, or even 12-inch wafers, which are a typical size for today's fabrication processes for micro-optical elements, not for semiconductor elements. Semiconductor elements are much larger, typically today 12-inch wafers. So 30 centimeters, 1 foot. And nanostructured surfaces, the smallest features we wanted to have are 400 nanometers. Why 400 nanometers? 400 nanometers is lambda over 2 when it comes to near-infrared applications, which are typical wavelengths that we have for sensors. So, and these are the necessary dimensions to realize reasonably diffraction efficiencies and a maximum size to suppress the first order in a zero-order grating application, for example, at 1064. 1064 is a typical wafer wavelength for an indium YAG laser. And of course, an industry would not like only to have plane surfaces. They wanted to have also these kind of surfaces on curved surfaces, as we have it, for example, at lenses. So to combine both diffractive and refractive elements. And the substrate and the grating material should be fused silica, so pure SiO2, and or optical glass, which is not pure SiO2, which is combined with some other metals or metal oxides in order to change the refractive index. And would like to have such kind of structures for applications from deep UV range, from 248 nanometers up to 1064, which is then the near infrared. So just to show you how we did we do that. Let us first start, how does it look like first? First, we start with a master in pure silicon. And I have to pay attention because in German silicon is not the same as in, no, silicon is correct, yes. Silicon, yes, is correct. Is it a master which is created in silicon is a rather rigid material, a brittle material, and we fill it out with PDMS, polydimethylsiloxane material, which is a polymer, to have a second kind of submaster by spin-on coating. Then by curing and demolding, we have this replicated flexible PDMS submaster. And this is how it looks like. You see, you can easily bend this. This is just like a foil. And you just peel it off when you produce it. And then you use this second flexible submaster. And again, you do a spin-on coating process. However, this time you use a so-called sol gel material, which is a special material, which is somehow a liquid glass. So in this liquid glass, you can afterwards also, by curing and demolding, transfer into hard material, so means in nanostructured SiO2 surfaces. That this works, I would like to show you now. So first, some words on the material. As I said, the materials we tested were several materials. First of all, for the flexible soft polymer submaster, we used, as I said, mainly PDMS, but we tested also PMMA and polyimide. These materials are plastic materials, especially known in classical optical industry. So we tried to find materials that they already know in industry, not to have something totally new, because new materials require new qualification processes, and this in return creates new administrational problems. So for the sol gel materials, we tested two different materials. The one was a polymeric sol gel processing, and the other one was a nanocolloidal sol gel processing, starting both first with a metal oxide compound. And in the case of nanocolloidal sol gel processing, we added some metal salts. And together then with the water solvent catalysts and hydrophilic polykondensation processes, we came up with these polymeric salts then, or in the case of the nanocolloidal sol gel that you can see on the right column, we then had some precipitates and then the nanocolloidals. And then by an annealing process, at the end, we have the glass. And so you see this annealing process already is a critical issue. Annealing means thermal treatment. Thermal treatment is always critical. As you may know, materials dilate when it becomes warm. Have you any idea how much glass dilates? How much metal dilates? A typical question that I ask my students when I have a pointing stick which is 1 meter long is, okay, imagine now I have this stick is 1 meter long. I make it 1 degree Celsius warmer. What do you think how much it becomes longer? Order of magnitude. I ask you, the students, what do you think? A stick of glass or a piece of glass 1 meter long by 1 degree of Celsius, how much does a glass stick becomes longer? You have an idea? Is it a millimeter? Is it a centimeter? Certainly not a centimeter, this becomes clear. But it must become longer, and this is typically in the order of several micrometers, depending on the material. So you see already here, we try to find out materials with a dilation coefficient, or so coefficient of thermal expansion, which is adapted to the ground material, and the ground material in this case was the master made of silica. So you see, these are ordinary questions we had to answer every day in order to figure out which is the best material. This is applied research. Theoretical research does not need to answer these questions because they are too stupid for them, because they try to find out the basic mechanism behind it. But here, when it comes to products, you have to answer such kind of questions. So then, let me see, what are the structures we had? I hope you see these concentric rings, more or less. These were the first samples for a so-called Fresnel lens array. And it looks not very spectacular on this level, but you see already here the scale bar is 1 millimeter. So from here to here is 1 millimeter. This is not nano, we agree. So now let us look closer. So you see, if you look closer to these structures, and we are now at a scale bar of 1/10 of a millimeter, so 100 micrometers. This is also not yet nano, but we see already there are structures there, so in principle the process works. The question is now, does this process really shows nanometric structures? And let us focus further in it. You see here there is a substructure in these general structures. So we focus now in, and we are again on this scale bar of 100 micrometers. And we can go even further. You see now, here again, we are now, the scale bar is 20 micrometers, and we can even see here these structures. These are the optical structures, these ones. You may ask afterwards, what is this? We come to this. And then if we look even closer, that's now a scale bar again on 20 millimeters. And if we look again closer, and here we are now at a scale bar of 5 micrometers, so 5,000 nanometers. And if we look at this scale bar, you see one ridge here is 400 nanometers. This was for us the proof to show really we could come down with this technology to structures at a region of lambda over 2 with respect to 800 nanometer as a rough magnitude. And the question now, as I asked already before, why do we have these strange structures? And I can tell you these structures were not foreseen at the very beginning. The question is, how did we produce our silicon master? The silicon master was created by a standard electron beam writer, and an electron beam writer is like an inkjet plotter. He works always like this, and these are the lines which are artifacts which comes from the master originally. But this is just a hint for us to see that our process to write our master is also a very critical issue that we did not take in account when we started with this research. We tried then other structures also, and other structures means gratings, cross gratings, as you can see here on the right side. These are just rectangular structures, and what is easy with such kind of rectangular structures, you can easily test it with every laser you have in your pocket. So just to show you how you test it, you just focus with a laser on it, you get this beautiful grating image, because these are all orders of magnitude, and so you can easily just project it on a wall, and you measure it just with a ruler on a millimeter or a centimeter scale. It's easy, but it's pure geometry. So you can easily detect it, and it's easy to test. You know, in this way you can also answer the question how to test diffractive structures. So this was the thing we did here. So this worked. So let us discuss now this technology. Nanoreplication of diffractive optical elements in spin-on glass technology has, of course, the potential to generate nanometrical structured surfaces in fused silica on both slightly spherical and plane surfaces. The slightly curved surfaces were possible because we had these flexible PDMS masters, which allow us to curve the surface also. However, on the other side, spin-on glass technology is currently too far away from industrial applications, and the reason for it, there is a strong material science impact. That's something we always cover when we come to nanotechnology. Materials and surfaces play an enormous role. And there is a saying, maybe I shouldn't say it in a Catholic university, that the devil, that God has made the solid body, however the devil has made the surface. And that's something, I would not say it's a theological thing, however, it is something you have always to keep in mind. Surface effects will always have an impact on nanotechnology, and that's something you cannot underestimate. And the described SOG technology has not enough potential to increase the process stability to a level of industrial production. This is another aspect. If you work in the field of optical elements, you have to have an excellent quality. You cannot never tolerate any defects. This would create an immense damage to the product first, of course, and then for the reputation of the company. So that's something they don't want to have. So let me now focus on another approach we had. This was a so-called node, project node. is a double sense word. Node means nano-optical devices and elements. And node, of course, means also a knot in a net of things. Here the partners was the micro-optics section of CSEM in Zurich, and again the PSI lab of Christian David. Let us now come to the thing you mentioned before, the so-called Maathai Effect, and you have all followed lectures in physics, I hope so. So you know probably not about the effective medium theory of zero-order gratings. Zero-order gratings means you have structures which are lower or smaller than the wavelengths of the light. And in this case, you do not transmit the higher order magnitudes. You just transmit your zero-order magnitude because the higher orders are all imaginary. So they are no more real. They are just to show you how it works. Here is a typical sawtooth or blade grating. So let us imagine there is a ray of light coming in with a yellow flash arrow under a certain angle theta 1. And then, of course, we know there are these diffraction orders which will come up. There's the 0th order, of course, which is just the same angle as the incident one, but there are the -0s one and the +0s one, and the transmitted one also at first the first two the zeros and the first order, and maybe also further ones. And if you calculate now the recording formulas, you will figure out if the structure, if lambda, the capital lambda, this is this letter, I don't know if you're familiar with the Greek letters, the big lambda is like A without a stroke in the middle, is smaller than the wavelengths of light, or typically smaller than lambda over 2, all angles for the transmitted and reflective orders are imaginary, so they are no more there. So that means we have just to fulfill this condition you can see on this formula. Then we have this condition for 0-order gratings. And now the question is, when it comes to production to these 0-order gratings, I showed you already the spin-on-glass technology we realized, but here the application was a different one because, again, material aspects become important. When it comes to deep UV applications, materials become very much attenuated, or they damp the amplitude of light. So we have to think about other materials which are transmissive at this order of magnitude. And typically here we have materials like SiO2 or calcium fluoride, which is a crystal. However, crystals do behave totally different when you try to structure them, because a crystal has a certain orientation of the atoms, of course, because it is a crystal, it's not an amorphous material like glass. So such kind of calcium fluoride devices are used, for example, as outcoupling windows for excimer lasers. I don't know if you're familiar with these excimer lasers. These are deep UV lasers used for various applications. Typical application wavelengths are 193 nanometers. And for such a 193 nanometers, to become a 0-order grating, we have to go down to 120 nanometers. 120 nanometers is rather small. And we have to have a depth of typically 40 nanometers. And a fill factor means the percentage of filled material to solid body material should be around 30 to 40%. And these people from the coupling window industry, they wanted to have a 3 millimeter to 5 millimeter area being structured at 100 nanometers and 120 nanometers. So it was a rather challenge. We just first started not to work on calcium fluoride because it's a difficult material. That's why we started to work with glass. As I initially said, glass has the advantage as an amorphous material. So chemical processing works more or less isotropic. So we don't have these anisotropic problems that we typically have for the crystals. So, and we also had an application at Leica, where I was formerly working, for spherical curved surfaces, as you can see on this picture. And what you see here, this blue and already greenish color, is not what you expect from your sunglasses. Maybe coating is a structure. It's a diffractive structure which has exactly the same function. And if you look on the surface on this barium crown glass, which is a BK7 glass, you see we structured it with a period of 270 nanometers. And the filling factor in this case was 60%, and the depth was 65 nanometers. And you can guess the scale bar here, this is 1 micrometer, so you can see these are really very tiny structures. To look at it a little bit closer, you see here how it looks like. So here you see the spacing between two ridges is 200 nanometers, or 270 nanometers to be correct. And if you look now at the sub-wavelength deep UV anti-reflective surfaces, we did a calculation and we did also a production. And you see here on the left bottom, here these 270 nanometers I just mentioned, and in fused silica on the right side, we did it also with the same process in 120 nanometers. And these are the results. This was an application for a wavelength at 365 nanometers, where we worked with fused silica. And you see the bottom line is without any coating. So you see typically 4% every physicist now, every glass surface absorbs at least or reflects at least 4%. So we said, okay, we have to come lower than 1% at least. If not, it makes no sense in relation to other classical technologies. And so we saw typically here the calculated results. These are the undotted lines. These are the theoretical lines, and these were the measured. So you will ask, why can the real product be better than the theoretical one? This is a typical question which turns out in problem when it comes to reality. Because theory is nice, but on a nano scale, nothing is like in theory. You think, and our model initially was a real rectangular profile with 90 degrees angles. But if we look, if you look here, we see here that this structure is beautiful, but it's not perfect. We have here a certain radius here on top. Here's a radius. This is not perfect 90 degrees. And then we approved our models. We said, okay, let us introduce now some radii, let us approach more smooth lines. And we found out, yes, then it fits. But initially, we started with a typical rectangular structure, ideally from physics, clear known. But you know, these are things we learned throughout the project. This is the difference when it comes to nanotechnology or if you speak about theory. So here is a 248 nanometer application, similar. You can see again here this situation. We have, these are the measured results and these are the theoretical results. So here you see already we improved our result. This is, the two directions are the two polarization directions, S and P. They're the polarizations, so don't be confused. In reality, this joins quite rather well. However, in theory, of course, there must be a difference because our grating was oriented in one direction only. Okay, so how did we produce now these gratings? We did it in a holographic lithography process, starting first with linear sinus gratings. They were just spin-on coated, as I initially already explained. This was done by projecting a standing wave or creating a standing wave on the surface by a helium-cadmium laser at 422 nanometers, focused on both sides with a pinhole with a lens just to create this surface and just to show how this looks initially. This looks like this. So the period here was 270 nanometers and depth was 30 nanometers. And then we metallized this under a certain angle in order to get somehow caps of metal on the top, and then we etched it. And then it looked first like that, and you see here already these structures here. This is glass, and this is resist material, so this is from the lithographic process. And all these things are brittle things for resist, which just break when we had it under the microscope. And we tested here various materials. So you see here, this is a typical float glass, this is a typical Bocron glass, and this is a flint glass, which is a special type of glass as well. And we had beautiful pictures we saw in the lab. You see here how are the results. And sometimes we had even such kind of funny things. And even here, for example, what happened? What do you think where we have these curved effects here? These are perturbances or elements or effects which came just by the change of temperature throughout the measuring time. And sometimes also we had some funny effects. We can't see it here because nearby the lab where we tested it was a railroad. And every time when the train came by, we had strong vibrations. First, we didn't know what it